Hello everyone. In this video, we are going to solve a simple problem on CPU scheduling, which has been asked in one of the GATE question papers. Let me now introduce the problem statement. Consider three processes, all arriving at time 0, with total execution time of 10, 20, and 30 units respectively. So now, according to the problem statement, I have three processes. Arrival time of all the processes is 0, and the execution time of each of the processes, say, let me say I have three processes, P1, P2, P3. So P1's execution time is 10, P2's execution time is 20, and P3's execution time is 30. Now our next part of the problem statement, each process spends the first 20% of execution time doing I/O, the next 70% of time doing computation, and the last 10% of time doing I/O again. So we know that the total time of a process is contributed towards both I/O burst and CPU burst. So according to this problem statement, the first 20% is for I/O burst, the next 70% is for CPU burst, and the last 10% is for I/O burst again. Now, the operating system uses a shortest remaining compute time first algorithm. So this is the scheduling algorithm being used, SRTF, shortest remaining compute time first. And it schedules a new process either when the running process gets blocked on I/O or when the running process finishes its compute burst. Assume that all I/O operations can be overlapped as much as possible. Now, our job is to find out the percentage of how long the CPU remains idle. So this is our question. We are given three processes. Their execution time is given and how they are executing, the order in which the CPU burst and I/O burst are given, that is also mentioned. The scheduling algorithm is given as SRTF, and the question being asked is, they are asking us to compute the percentage of CPU's idle time. Now let's move into the problem solution. Now, based on the given statement, as I told you, we are going to consider three processes, P1, P2, P3. Their total burst time. Burst time means the execution time. Okay. So total burst time, according to the given problem statement, for P1 it is 10, P2 it is 20, and P3 it is 30. According to the problem statement, it says first 20% is for I/O burst, next 70% is for CPU burst, and the last 10% is for I/O burst. So how do we do this calculation? See, the total execution time of P1 is 10. So out of 10, first 20% is for I/O burst, which means 2 milliseconds for I/O. The next 70%, that means 7 milliseconds for CPU burst. And the last 10%, which means last 1 millisecond is for I/O burst again. So this is how the I/O burst, CPU burst, and I/O burst again for P1 is computed. So if you add up all these three, that is 2 plus 7 plus 1, we get 10. So in a similar manner, we are going to do for P2 as well as P3. So when you do it for P2 and P3, 10%, the first 20% is for I/O burst, right? So 20% of 20 is 4. 70% of 20 is 14. And 10% of 20 is 2. Okay. Similarly, do it for P3. P3 is 30. So P3's total burst time is 30 milliseconds. First 20% is 6. Next 70% is 21. And last 10% is 3. So that's how we get for P3. So from the given data, we have now computed the I/O burst, CPU burst, and I/O burst for each of the processes P1, P2, and P3. Now let's apply the algorithm. The algorithm given to us is SRTF. So based on the SRTF algorithm, I am now going to show the Gantt chart. So this is the Gantt chart. The scheduling algorithm that we are using is shortest remaining time first. Okay. So according to the algorithm, according to the given problem statement, it says that the first 20% is contributed towards IO. That means P1, for P1, the first 2 milliseconds, P1 will not do anything. Okay. Similarly, the first 4 milliseconds, P2 will not do anything. Similarly, for the first 6 milliseconds, P3 will not do anything. So that is what is shown here. Now, when the time 2 comes, immediately P1 will start executing and P1 will be executing and it will be continuing its execution on the CPU. So its total time is 10 milliseconds. So the entire amount of time P1 will be executing, and as you continue drawing the Gantt chart, okay, we know that the last 1 millisecond of P1, that is P1 will now execute for a total of how much time? See, according to our solution table here, P1 first 2 milliseconds is not doing anything. Then 7 milliseconds only it is executing. So for 7 milliseconds, that is from 2 to 9, up to time 9. That is from time 2 to time 9. So 9 minus 2 is 7. So 7 milliseconds P1 only will be executing. The remaining 1 millisecond during this time from 9 to 10, P1 will be doing nothing. Right? So with that, P1 will complete and leave. But from 9, P2 will start its execution. So from your table, what is the total time for P2 on the CPU? The total time for P2 on the CPU is 14. So what is 9 plus 14? What will you get? You get 9 plus 14. You get 23. Right? So up to 23, P2 will be executing on the CPU. Once P2 comes out, P3 goes in next and P3 will be executing on the CPU for 21 milliseconds. So 23 plus 21 is 44. So the remaining part of P2 will be not doing anything. That is doing IO for the remaining 2 milliseconds. And similarly, P3 will be doing IO for the last 3 milliseconds. So during this time again, the CPU is idle. So for the first 2 milliseconds, CPU is idle. Similarly, for the last 3 milliseconds, CPU is idle. So according to this Gantt chart, the CPU is idle for totally 2 plus 3 milliseconds, which is nothing but CPU is idle for 5 milliseconds. 5 milliseconds out of how much is the total time? The total time is 47. So out of 47 milliseconds, 5 milliseconds, the CPU is idle. So how do we compute the percentage? Percentage is computed as 5 by 47 into 100, which is nothing but 10.638%. So this is how we compute for how much time the CPU remains idle. I hope this video was useful to you. Thank you.